15 talks about simple harmonic motion. So I'm going to introduce to you what is a simple harmonic motion, which is mainly the description of mass and spring system. Mass attached to a spring, and I'm going to describe the motion of mass attached to a spring, and we call that motion simple harmonic motion. And this is a simple mass and spring system. You have a spring that has a spring constant K attached, and if we attach to it a mass M, and if we assume that this surface here is frictionless, and if we push that mass a little bit or compress that spring a little bit, and if we let go of that mass, it will move, it will oscillate forever. It will never stop, as long as there is no friction on that table. Now we need to describe the motion of that mass. And to describe the motion of that mass, we need three quantities, three physical quantities. Can you tell me what are those three physical quantities? Minna? Yeah, three physical, the motion of that object.
The decay of the spring?
There is no decay because there is no friction, so it will continue, move forever. If we give it a push, it will oscillate forever. It will never stop.
And the mass?
No, that's not. We don't need that to actually really describe direction of what? The motion. We need the displacement. That's one. We need the displacement to fully describe the motion of any object. We need displacement. We need velocity. We need acceleration. To fully describe the motion of any object, we need displacement as a function of time. We need the velocity as a function of time, and we need the acceleration as a function of time. If we know those three physical quantities, then we would be able to find the position of that object at any point of time. If I tell you the velocity, the initial position, and acceleration, we will be able to predict the motion of that object. And that's what we want to do in this. So now I have a mass and a spring system. Mass attached to a spring, and we need to find displacement. Any idea how to do this? How can we describe the motion of that object? Taha? Taha? What should I do to describe the motion of that object? Ashur?
Measures the distance from the wall to the
Okay, and?
equation.
I cannot measure anything. I want to actually find an equation now that describes the motion of that object.
Isn't there is an equation which is half kx squared?
What's half kx squared? That's the kinetic energy, that's the potential energy stored in the spring.
And the mechanical energy is equal to the kinetic energy plus the potential energy, right?
Can I take you a little bit back to chapter 5? When we had an object that slides down that plane, that surface, how did we describe the motion of that object? What did we do? Different components for what? Of what? Of what? Of the mass? Of the forces. So what did we do first before we do this? We draw the free body diagram, then we put all the forces acting on that object, then we have specified our coordinate system, and we resolved the forces according to our coordinate system, and we applied Newton's second law, then we were able to find the acceleration. Right? So I'm going to do exactly the same. Free body diagram. What are the forces acting on that object? Mg down M. I wouldn't really call it T. It's the force of the spring. and we gave it a name, if you remember, the restoring force. And restoring force because actually it always pull that object back to the equilibrium position. So this is this is the spring, and this is the mass attached to it, and this is the equilibrium position. If you push that and you let go, the spring will pull it back to the equilibrium position, and if there is no friction, it will continue moving in that direction by inertia, Newton's first law. Then it will stop, and what happens? The spring will push it back to the equilibrium position, will continue move after it goes through the equilibrium position, it will continue move to the other direction, and it will oscillate forever. It will never stop if there is no friction. And we're going to assume that there is no friction for now in this course. Okay, guys? So that force, the restoring force on the spring. Now, I want to describe that motion, which is the motion along the x-axis. Then I should not really worry about the forces along the y-axis, as if they are not there. They will not affect that motion along the x-axis. Now, let's apply Newton's second law. Vanessa? Fx equal ma. Force, restoring force from the spring equal mass times acceleration. What is the restoring force from a spring? Hooke's law? Hooke's law? No. Minus kx. Fx equal minus kx. It's the force constant times the displacement, and the negative sign means that the force and displacement are always opposite in direction. If the object moving in that direction, the restoring force will be in the opposite direction, and if the object moves in that direction, the restoring force will push it back all the time in that case, and that's why we put that negative sign. So that's Newton's second law. We have applied now Newton's second law. Then what? Then what? Then I'm going to replace that acceleration by its differential form. That acceleration, I will write it dv by dt. Or d2, so I'm going to write a equal to dv by dt, guys, right? Or a equal to d by dt for the velocity. This is the same thing. I'm going to replace the velocity by its differential form as well. So this can be written as d2x by dt squared. It's the second derivative of x with respect to time. This is the acceleration. So I'm going to replace acceleration by its differential form. Okay? And I would rearrange that equation. So I'm going to say that it's d2x over dt squared plus k over m x equal to 0. Can you follow what did I do? I divided the whole equation by m. Minna? I divided the whole equation by m. Then I moved that term to the other side. I got that equation, which is d2x by dt squared plus k over m x equal to 0. That k over m, that really bothers me. So I'm gonna give it another name. So that k over m, I will give it another name. Anyone would like to volunteer, give it a name? Who wants to name it? Yeah, I can do that, but I have used x already. Yeah. If you insist. Anything. Doesn't matter really. Okay? How about I call it omega? Omega, and I will tell you why I will call it omega squared. Which means, if I call it omega squared, that means that omega, whatever omega is, doesn't matter now, is the square root of k over m. Okay? So I'm going to replace that k over m, and I will put instead of here omega squared. Now, did anyone talk differential equation? Did you guys study any differential equation? Did you study differential equation? Sharif? Okay. So that equation, that form of equations, we call it differential equation. It's second order differential equation. And if we solve that equation, we will be able to find x as a function of time. This is what we'll find. If we solve that equation, solving that equation, that's calculus 200 something. And I will not go there. But trust me, for now, the solution of that equation is the following. It's a sine omega t. How do I know that? That's how we solve the differential equation, and we're going to study that in calculus 200, something in calculus 200. But that's the solution. How can we make sure that this is really a solution? Simply take that x, find the derivative of that x twice, put it in here, and put the value of x in here, and see if d2x by dt squared plus omega square x equal to 0 or not. And let's do that together. And if I can actually verify that this equation satisfies that differential equation, then this is a solution for that equation. So let's find the derivative of that x of t. Equals. What is the derivative of that equation? A is a constant. By the way, A is a constant. Omega is a constant. We're doing the derivative with respect to time. So I'm going to do this. dx by dt. It's A. The derivative of sine omega t, that's cosine omega t, times the derivative of omega t with respect to time, so omega. So we get A omega cosine omega t. But actually we need the second derivative of x with respect to time. So I have to do that one more time. I have to do that derivative one more time. So d2x by dt squared equal to A omega are constants. Here they are. Thank you. Negative. Here is the negative. Sine omega t. Did I miss anything? The derivative of omega t with respect to t will give us omega. So we get minus A omega squared sine omega t. So that's d2x by dt squared. Now let's verify that equation. So minus A omega squared sine omega t plus, now I have written d2x by dt squared. This is the first term. Plus what? Omega squared, that's there, times x. Equals to, yeah, minus A omega squared times sine omega t, and here we have positive A omega squared sine omega t. That's 0. So this is really a solution of that equation, which means that the motion of that object as a function of time will follow that equation. The motion of that object as a function of time, that object will follow that equation. It's some constant multiplied by sine omega t. So if I want to actually draw the displacement as a function of time, if I want to draw the displacement as a function of time, this is going to be the displacement as a function of time. X t. At time equal to 0, what's x? What's sine 0? 0. So x is 0. Okay, guys? And this is going to be mainly sine of something which is omega t multiplied by a. So this is what happens. This is the motion. X, the displacement, increases with the time. Then it decreases again with the time, goes back to 0, and it reverse direction. Displacement increases with the time, then start displacement to decrease again with the time. Look at the motion, the spring and the mass. Displacement will increase with the time, then it stops, it goes back, so it decreases with the time till it goes to the equilibrium, which is back to 0. Then it reverse direction, which that means it will increase, displacement will increase with the time, but in the opposite direction. Then it stops. Then it will decrease with the time and goes back to 0, and it repeats itself. And it repeats itself. So this is a description of the motion as a function of time. Okay, guys? We call that motion a simple harmonic motion. And definition of a simple harmonic motion is in here. Is in that equation. If you have the acceleration proportional to the displacement with some constant, which is omega, and in the opposite direction, we call that a simple harmonic motion. We call that motion as a simple harmonic motion. Why are we studying this? Why are we studying simple harmonic motion now? We have studied linear motion, which means an object that moves in a line. We have studied circular motion. An object moves in a circle. This is a combination of those two motions. An object that seems to be moving along the line, but it's actually performing a circular motion. It starts from a point, goes to a point, to maximum, goes back to the same point. It's as if you have a point that rotates in a circle. Starts from a point and it rotates, go back to the same point. It's the same thing. An object that starts from a point and it oscillates around that point. So actually this is a combination of the two, linear motion and the circular motion. That's the simple harmonic motion. And the definition of a simple harmonic motion, it's a motion where you have the acceleration directly proportional to the displacement and in the opposite direction. Okay, guys? So now, what is the displacement as a function of time? Simply, it's A sine omega t. Someone will say, how about cosine omega t? How about A cosine omega t? Will that work? Will that work? Yes or no is based on the same thing we have done on that part. We're going to repeat it again. We'll find d2x by dt squared and plug it in here and plug the value for x and see if you add them together, those two terms together, if they add up to 0, then yes, A cosine omega t is a solution, another solution for this. Let's try it. So I'm going to assume that this is, instead of sine, it's cosine omega t. Nada? It's a cosine omega t. Let's find the first derivative of that equation. So it's A, instead of sine, the derivative of cosine, that's sine, negative sine, omega t, and the derivative of omega t, you it gives us omega. The second derivative, nada. I'm going to do that again. Minus A omega, constant. Minus A omega is constant. The derivative of a sine, that's cosine omega t, and the derivative of omega t, you get your square in here. So that's the second derivative of x as a function of time. Now let's substitute in that equation there. d2x by dt squared. This is the whole thing. plus omega squared, here it is, times x. Do they add up to 0?
No, yes.
So again, this is another solution for that equation.
What's the difference?
Very, very good question here. What is the difference? What is the difference? Initial condition, something that we call it initial condition. Initial, when you enter, let's assume that I have ran that demonstration for some time. Then you walk to that classroom one by one. Farida walks in first, and she finds out that when she gets into the room, that point, that object is at the equilibrium position. Which means, you see, what did the talk say? At time equal to 0, x equal to 0. Which equation should I use? I have two equations, I have two solutions, and I should choose one of them that represent that motion now. So when Farida came in, she had the option to choose between x as a function of time equal to a sine omega t and a x as a function of time equal to a cosine omega t. When Farida came in, which is time equal to 0 according to Farida's watch, at time equal to 0, x, she saw that object at equilibrium position, which is x equal to 0. So she should use that equation. Later on, Minna came to the class a few minutes later or a few seconds later, and when she walks in, she finds that object at the maximum displacement in here. Which means that at time equal to 0, what's x? Maximum. What's the maximum value for x? Look at the equation, any one of them. What is the maximum value of x? Either this equation or that equation. The maximum value is controlled by that term, sine omega t or cosine omega t. When this is maximum, because this is the oscillating term in that equation. When this is maximum, x is maximum. When this is maximum, x is maximum. What is the maximum value for any sine function? 1. What is the maximum value for any cosine function? So what is the maximum value for x? A. When actually Minna came in, at time equal to 0, x was equal to A. Let's find out. At time equal to 0, what's the cosine omega t? 1, because t is 0, omega t is 0, cosine 0 is 1, so this Minna should use that equation. So actually, how come we have the same object that moves in the same motion, and Farida described it by an equation, and Minna described it by another equation?
But they both get the
But they both get the same
same answer.
answer. And when we go and study Calculus 200, they will tell us if you have a differential equation and you have a solution to that equation, and you have another solution for that equation, that means by default the addition of those two solutions is a solution of that differential equation. So if I add cosine omega t and sine omega t, I should get the same solution. So let's see in here, what did I do? So take a breath now. We're going to review what we have done now very quickly. So you can finish. Write that down. Write it down. That's a simple harmonic motion. I drew the free body diagram. I applied Newton's second law. I replaced the acceleration by its differential form. Then I got that differential equation. And when we get the differential equation, we said that solving that equation will give us x as a function of time t. And if we get the x as a function of time t, we will be able to describe the motion of that object at any time. And we said that the solution for that equation is a cosine omega t. That's a solution for that equation. And to make sure that this is really a solution, I find the first derivative of that x, then the second derivative of that x, then substituted in that equation by the second derivative and x, and we got that. Actually, it verified the second equation. Then someone else said, well, how about sine omega t? Sine omega t can be also a solution. Let's find out. So what we did is we verified that a sine omega t is another solution for that differential equation, which means that the linear combination, the addition of those two equations, a sine omega t and k, any other constant, p sine omega t, is a solution. This is the addition of the two solutions. This is also a solution. Let's look at that equation in a little bit more details. dx by dt, I'm going to verify that this is also a solution. So I'm going to say dx by dt is blah, blah, blah. d2x by dt squared, this is the second derivative of that equation, is that. And if you put that in that equation, that differential equation, once more you will find that actually it verified that equation. I'm going to introduce something to you guys a little bit now to convince you that this is also a solution for the z differential equation. Look at that equation. X equal a cosine constant omega times t plus, I'm going to add another constant in here. This is the cosine of two angles. Cosine of the addition of two angles. I'll tell you why. I'll tell you why. Why did I add that phi in here? And what does that phi mean in a minute? So now I'm going to add that phi in here. This is the addition of two angles, right? So actually I can actually replace that cosine omega t by a constant times sine omega t plus c cosine omega t. What I really did is the following. I say that x equal a cosine omega t plus phi, which means that x equal to a times cosine omega t times cosine phi minus a sine omega t times sine phi. Cosine theta 1 plus theta 2 equal to cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2. Do you know that rule? Do you know it? If you don't know it, just take a note of it, and if we need it, it's going to be in the exam, in the formula sheet. But we're not going to need it. This is just for your knowledge. No, you have to wait with me. You cannot leave.
I have a deadline on my registration.
Okay. Okay, guys. So can I do this? I'm going to call a times cosine phi. Since phi is a constant, then cosine phi does not depend on the time. Phi is a constant. It does not depend on the time. It doesn't matter. At time equal to 0 or time equal to infinity, cosine phi will remain the same. A will remain the same. So a cosine phi, I will give it another symbol. I'm going to call it c. So now a cosine phi, that's c cosine omega t. Here is the omega t. And a sine phi, I will call it b. Then you get this solution. X equals c cosine omega t plus p sine omega t. This is that. So actually, adding that phi means something physically. What does it mean? First of all, look at that equation. This is the general solution. This equation is the general solution for that equation. This is the general solution for that equation. Look at that equation. X equal a cosine omega t plus phi. What's a? The maximum displacement. A, we got that a minute ago, it's the maximum displacement. And people in physics and mathematics and engineers, they call it the amplitude, which is the maximum displacement. The maximum displacement, the amplitude of that motion. One. omega t. What is the units of omega t? Unitless, it should be an angle, it's unitless, which means that what is the units of omega? 1 over time, it's the units of 1 over time. What physical quantity that has a units of 1 over time? Frequency. What's omega? It's the frequency of that motion. It's how many oscillations that object makes in 1 second. That's the meaning of omega. So omega is the frequency of that motion. So now we know what's A. We know what is omega. The remaining part is phi. What is phi? Yeah, phase. Phi tells us, phi makes us able to use the same equation. So can Farida and Minna use the same equation to describe the same motion of the object. Let's try this. Let's try this. Now I'm going to erase those two equations, and I will write the general equation, which is x as a function of time t equal to a cosine omega t plus phi. Again, a is the amplitude, omega is the frequency, angular frequency. Now we need to find out what is phi. Farida came in at time equal to 0, and she found that x is equal to 0. The particle was at the equilibrium position. Let's do this. Let's apply those boundary, we call that boundary conditions in that equation. 0 equals to a cosine phi, because t is 0. So omega t is 0, 0 plus phi, that's phi. Which means that cosine phi should equal to 0. What's phi? Cosine phi in that case should equal to 0, which means that phi should equal to pi over 2. Now we know that Farida should use that phi in her description. Sure. When Farida came into the class, she found out that that object is at equilibrium, and that was at time equal to 0. So I call those boundary conditions. We call them the boundary conditions, or initial conditions. So the initial conditions told us the position of that object at time equal to 0. This is the meaning of initial or boundary condition. So at time equal to 0, put 0 in here. This gives you 0, and you get here cosine phi. X was equal to 0 at that time, so put 0 in here. Now 0 equal to a cosine phi. A cannot be 0. A is the maximum displacement. And the maximum displacement is a, it's some value. It cannot be 0, which means that cosine phi has to be 0. What is the angle that gives you that its cosine is 0? Pi over 2. So now we know that Farida should use that phi in her description, and she should use that same equation. So now Farida, when she goes and describes that equation, she should write this: x as a function of time t equal to a cosine omega t plus pi over 2. Yeah, thanks so much. Turk said, but we know that omega t plus pi over 2, that's cosine omega t plus pi over 2, it's a sine omega t, which is the same equation Farida used before we come up with that general equation. True. Remember, when it's still in here, I wrote x as a function of time t equal to a sine omega t, and that was the equation that Farida used a minute ago. Vanessa, would you please move in here? Okay. So what happened is Turk is saying, but we know that cosine omega t plus pi over 2, cosine any angle plus 90 It's the sine of that angle. So those two things are totally the same.
So we could do this if in the case only if phi is equal to
Yeah. Yes. Now, let's look at Minna's case. When Minna came in, what happened? When Minna came to the class, she found out that her boundary condition, her initial condition at time equal to 0, x was equal to a. She found that object at the maximum displacement. Now, look at that equation again. This is the general equation that we have. At time equal to 0, that means that a times cosine phi should equal to
x of
a. No. What was the position when Minna came to the class? A. Which means that that equation tells you that cosine Bishoy. It tells you that cosine phi equal to? Great. If cosine phi equal to 1, what's phi? Phi in that 0. In that case, Minna in her description, she should use that equation. I will write in here, x as a function of time t equal to a cosine omega t plus 0. Now they are using the same format, same equation, but each one of them is using different phi, different phase. And that phi tells us that the boundary condition is different from one to another. One of the two guys came in a little bit late. She did not catch the object at equilibrium. She caught that object at some other angle.
But in all cases, t equal to 0.
That's the initial condition. Now we don't have t equal to 0. Nada? In that equation, Farida's equation, Farida can actually use that equation. At any time, give her the time, she will tell you what is the position of that object. Okay? And Minna, tell her the time, she will give you the position of that object.
But this equation only gets the position, does not get the acceleration or the velocity.
Oh, that's a very good observation. True. But that equation, that red equation, it gives you only the position. It does not give us acceleration or velocity. Amiro, yes. I'll answer that in a minute.
When x equals 0, the method is the object going that way or that way?
No. No. It's 0. Its position is 0. Doesn't matter.
If it's going that way, then the x will be,
It's 0.
when we calculate any other.
You're asking, you're trying to say, well, when x equal to 0, can I find the direction of that object if it's going to the right or to the left? Yes, but not from that equation. From the equations that Nada actually wants us to get, which is the velocity and the acceleration. Okay, Nada, now forget about Farida's and Minna cases. We're back to square one. This is the general solution that describes a simple harmonic motion. Simple harmonic motion. Position of the object that moves in a simple harmonic motion. Sharif, let's find the velocity. Back to chapter 2. Definition of velocity. Oh yeah, thank you. Let's do it one more time. It's not gonna hurt us if we do it one more time. Actually, Vanessa is gonna do it for us.
This is the one which is there is only one of the two equations that we use. Is the
We're gonna do it for that equation. For the general one, Vanessa. She has to figure that out. I forgot your name. Oh, Yahya. She cannot answer because you were talking to her all the time. Vanessa. No, yes, of course you know it. Trust me. Trust me more than you trust yourself. I know that you know it. A is constant. So, and this is a function of time. So A goes down. The derivative of any cosine, it's negative sine. Omega t plus phi. Then the derivative of that with respect to time, which is omega. Now you have the velocity. Okay? Acceleration. If you tell me the acceleration, how can you find the acceleration? Differentiate the velocity. So acceleration will equal to dv by dt, which is also d2x by dt squared. Minus negative a omega cosine the bracket omega t plus phi. Am I missing something? Times omega. So now we have displacement, velocity, and acceleration in three colors. Let's draw them. Yes, as a function of time. Let's look at them as a function of time.
I have a question. We use it in the same, if you want to get the velocity or acceleration, we use the same way to get the phi and then solve the equation.
Of course, yeah. You have to deal with the boundary condition, and if the boundary condition is giving you the velocity at time equal to 0, then you use that equation. If it's giving you the displacement as a function of time, at time equal to 0, you use that equation. If it gives you the acceleration, you use that equation. So it depends on the boundary condition. Amira?
We have to know omega and a.
Of course, that's why we call those three quantities, A, omega, and phi, we call them the constant of motions. The constant of motions, which means that if you tell me what's A, what is omega and what is phi, I can describe to you the motion of that object at any time. If you tell me those three constants, A, omega, and phi. Yeah, and I said at the beginning that omega squared equal to k over m. So omega is a function of k and m. If you tell me the force constant of the spring, and if you tell me the mass of that spring, I can tell you what's omega. A is the maximum displacement.
Which is a square.
Maximum, and we have to get that in order to describe omega and phi. I have to give you those to fully maximum displacement is A, to fully describe the motion of that object.
You plug in phi either 0 or pi over 2.
No, phi can be anything between them. Phi can be, I gave you two extremes, but phi can be 1 degree, 2 degrees, 50 degrees, can be anything.
So what's for representing the motion?
It represents to you when you came in, when you first want to describe the motion of that object, where was that object at? At equilibrium, then phi equal to pi over 2, maximum displacement, then phi equals to 0.
So it's not like omega or A or anything
No.
related to the motion.
No. Now can we draw those three equations, which is x, v, and t, and A. And the reason for this, I want you to look at that's the x-axis, the y-axis, that's the x-axis is the time. Okay guys, displacement first. Displacement, velocity, and acceleration. Three quantities. Displacement. It's a cosine angle. which means that at time equal to 0, x, I will assume for the three of them, in order to be able to draw them, that phi is equal to 0. Phi is equal to 0. So at time equal to 0, x equal to a. So this is the motion. A. At time equal to 0, x was equal to a, then it goes to 0, reverse direction to negative a, it goes to the other side, goes to a, it starts from here, from the maximum displacement, then it goes to 0, then it continues to the other side, negative a, it goes back to 0, then it goes back to a. This is one complete cycle. That's displacement, the red color. The blue color, velocity. At time equal to 0, what is the velocity? At time equal to 0, what is the velocity? Again, we assume that phi is equal to 0. This is going to be 0. Sine 0 is 0, so the velocity is 0. Then what happens? It peaks, goes down. Oh, thank you so much. Who said that? Yeah. Ashur, you're right. Ashur is saying, well, you should not start from maximum value in here. You should start from the negative because of that negative sign. So I should start actually from here, somewhere in here. Here, 0, then go down. You have to align it to 0 at maximum, then peak again, 0 in here. This is the peak in here at 0. Sorry, no, this is the peak. So that's the velocity. So this is the velocity. Before we go to the acceleration, what is the maximum velocity? No, I'm not asking about the position when you get maximum velocity. What is the maximum magnitude of the velocity? Well, Mustafa is saying, well, the maximum of that whole thing is when that sign is maximum. Yes. Yes. Sine goes from 1 to 0. Maximum value for the sine is 1. Then it goes to 0, then to negative 1. So the yeah, of course, I know. So the maximum value of this magnitude. So forget that. When I say magnitude, you forget about the sign. Okay? So the maximum value for this is when this is maximum, when the sine function is maximum, and the sine gets maximum, its maximum value is 1. So this is a omega. So the maximum, x maximum equal a, v maximum equal to a omega. Now let's draw the last one, the acceleration, then find the maximum value for the acceleration. Acceleration. Well, acceleration should look like exactly like the displacement, but it should be multiplied by omega squared and negative. So if this is here, if that's the displacement, then the acceleration should be somewhere in here. It's the same cosine curve. It's the same cosine curve again, but it's inverted because of that negative sign.
Why are we not putting why
So-
is omega and omega squared affecting the graph?
It's good.
You couldn't is velocity affected by omega with omega squared?
What? Yeah, but it can be also, omega squared can be a ratio, can be 0.2 if it can decrease. It's just a constant. But the most important part is the value for A here is, for the displacement here is A. The value for velocity in here, maximum velocity here, that's A omega. The value for this in here, that's A omega squared. The maximum acceleration, look at here, that equation. The maximum acceleration happens when this whole thing is maximum, and that whole thing gets...
So A omega squared is greater than omega, or greater than A, or less than A?
Yeah, omega squared can be 0.999.
Oh, it's never going, and it's going to be near.
It can be anything.
So
It can be more than that or less than that. It can be, it's just a factor. This can be 100. It can be 0.1. It can be 0.9. So in that case, it's 1. Okay? Okay? So, you know, on the, you know, I'm really bad when it comes to drawing. But you'll see the curve on the PowerPoint presentation much more prettier than this. Okay, guys? So those are the three values. And now you can find the maximum value for each one of them. Simply happens when the cosine or the sine term is 1. Okay. So this is the one complete wave of displacement as a function of time. The one complete wave, this means that this whole thing, one period, one whole wave, it has a periodic time of 2 pi over omega. And that's the meaning of phi. At time equal to 0, the object was not at the maximum displacement, nor at 0. It was somewhere between them. This is at time equal to 0. That's why we know that phase difference. That's phi. That's the meaning of phi. Phi in that case, in that graph, it's pi over 2. And phi in that case is a little bit different than pi over 2. I'm going to skip that example in here. You can read it, but doesn't matter. If we have a mass and spring system horizontally or having it vertically, if having it oscillate that way or oscillate that way, no. The physics is all the same. The physics is all the same. The equation that actually describe the motion of that object is always the same. The only difference is the equilibrium position in that case has no extension. The spring is not extended, nor compressed. This is the equilibrium position. But if you do it that way, the equilibrium position, because of the gravity, will be at some x. This is your 0x. So your 0x will, your zero initial position, the initial position will be shifted a little bit. That's all. Amira?
But when it goes up, there's two forces. That will be
Mm-hmm.
only one force
True, true.
will be at x.
Yeah. And when it goes down, you have the same, two forces. You have the restoring force from the spring, and you have the gravitational force as well. Now, if a gravitational force is acting on the object no matter what is the direction of the motion, right? If it moves up, what is the gravitational force on that object? In what direction? When it moves down, what is the gravitational force on that object? mg. In what direction?
So when it moves up, the direction of the two forces are not the same, are different, and move down in the direction.
Yeah, but that will not affect anything. This is what's going to happen in here. When you do this, when you apply here, at any point in time, you apply Newton's second law, which is that minus ky minus mg equal to 0. So now what I'm going to do is a very famous trick. All mathematicians know, nada. All mathematicians know, and they call it we're going to shift our coordinate system a little bit. So instead of calling this y, I will call y, I will divide that whole equation by k here. Look in here. So I'm going to replace f by its value. It's m times d2y by dt squared. And in here, I'm going to multiply, I'm going to take k as a common factor from that equation. I'm going to take k as a common factor. If you take k as a common factor, you get k out. The remaining part is y. There is no k in here, so actually as if you divide by k. And I'm going to call that whole thing, y prime, y1. So it's mainly I shifted y position by that magnitude, by that amount. And the same equation will apply. Okay? Torque, I'll go back to you. Okay? Torque. Yeah, you're right. There's a mistake in here. This should be plus. But that does not change anything. You just shifted your y, your origin by a small amount, which is mg plus k, to the left or to the right, doesn't matter. But the same equation. So if you replace that variable by the new variable, which you call it y1, you have the same equation again. Minus k, oops. I'm going to call it u in here. I will call it u. So then you get minus k u equal to m times d2u by dt squared. Again, that's the same differential equation. If you solve that differential equation, you get the same solution. More important than okay. More important than saying that example in here, let me tell you something before we leave. Someone today said that there is a quantity that's half k equals to half kx squared. And I commented that this is the potential energy stored in the spring. That's the potential energy stored in a spring. It's equal to half kx squared. If you have a mass and spring system that moves, from the energy point of view, what happens? You start from zero, at zero equilibrium, then you push it a little bit, then you let go. When you pushed a little bit, what did you do? From the energy point of view, you gave the system some energy, and it is stored in the system now as a potential energy. When you let go of that mass, what happens? That potential energy will transform into kinetic energy. That's why the object will move. The kinetic energy will transform back to potential. The potential energy will transform to kinetic energy till it goes to equilibrium, and at equilibrium, all of the potential energy has been transformed into kinetic energy. Then what happens? That object will continue to move to my left, transforming the kinetic energy into potential energy. Then it compresses the spring, it stops. Now we have all that kinetic energy transformed into potential energy. Then it gets fired back. So the potential energy, it gets transformed again into kinetic, potential, kinetic, potential. So at the two ends, you have maximum potential energy because X is maximum. X at the two amplitudes is maximum. You have maximum potential energy. At equilibrium, you have maximum kinetic energy. And between maximum points, maximum displacement, and equilibrium, between them, you have a combination of the two energies, potential and kinetic. What is the total energy of the system? Can you tell me what is the total energy of the system? Can anyone tell me? Can you give me actually a quantity for that? Can you quantify that? Can you give me a number of that? Not a number, but symbols of that. Can be. That's not the maximum.
The maximum?
Yeah, I need the maximum.
1/2.
Sorry, I'm sorry. I need the total energy for that system. Total energy of that system. No, it's not zero. Because it's not zero, because when you pushed it, you gave it some energy, so it's not zero.
You can have half mv square at the equilibrium.
Okay, so Amira said, well, if you calculate the half mv square at the equilibrium, this, since at equilibrium all the energy is kinetic energy, then we can find the total energy. I'm going to extend that assumption a little bit more. If I calculate the potential energy at one of the ends, this is the total energy. Half k, so potential energy is equal to half kx squared. At the ends, x equal to a. So the total energy for the system is half k a squared. Half k a squared. A is the amplitude. And actually you can verify that either by concept as we did now, or you can say, as you did a minute ago, that the total energy equal to kinetic energy plus potential energy. Kinetic energy, that's half mv squared. Here's your v, put the value for v squared, plus potential energy, which is half k x squared. Here is your x. Plug in the values for v and x, and if you do this, you will find that the total energy is equal to half k a squared. If you do it, actually it's on the slides. Okay, guys. So this, I would recommend that you study chapter 15 from the slides, not from the book, because I have actually summarized that chapter a lot. This is the end of chapter 15. That's everything in chapter 15.